In this session, we'll discuss about an impulse invariance method. In the design of IAR filters, what we'll do, first we'll design analog filter H of S, then we'll transform H of S into H of Z, that is digital transfer function. But how to transform it? So there are transformation equations, the transformation methods are there. So in this impulse invariance method is one of the popular transformation method to convert H of S into H of Z. In this session, we'll derive the expressions or equations to transform our analog H of S into H of Z. Let us assume you have an analog transfer function H of S. H of S is A1 by S minus P1 plus A2 by S minus P2 and so on, An by S minus Pn. So this is an nth order analog transfer function. So I'll write it in a simple form using summation, that is k is equal to 1 to n. You can write it as ak by s minus pk, right? So to find out analog analog impulse response, that is h of t, we need to apply inverse Laplace transform on both sides. So if you apply inverse Laplace transform, what you have? Apply inverse Laplace transform, right? What we have, this is h of s is equal to sigma k is equal to 1 to n. So ak is constant. You can write L inverse of 1 by s minus pk. So you know the formula of L inverse of 1 by s minus a. You can write it as e power this at into u of t. I'll use this formula here. So here I can rewrite this expression, k is equal to 1 to n ak L inverse of, what you can write, inverse Laplace transform of 1 by s minus pk. I'll use this formula. So using this, pk is a in place of a, you have a pk. So I can write e power pk into t into u of t. This L inverse of h of s is h of t. Now you'll find out h of n by sampling t equal to nt, by sampling t at t time interval. So you can write t nt is equal to sigma k is equal to 1 to n ak e power pk. So your t is nt into u of nt. You know Z transform formula, h of z is equal to, write it, n is minus infinity to infinity, your h of n and z power minus n. If you apply this formula, h of z formula for h of n, what I will get? H of z is equal to sigma n is minus infinity to infinity. What is h of nts here, right? We have nts sigma. I'll write it in a different color. This is k is 1 to n e power pk nt u of nt and z power minus n. Once again rewrite this expression. I can write sigma k is equal to 1 to n. I'll write ak here. I think there is ak. I can write ak here, and sigma n is minus infinity to infinity e power pk nt into u of nt z power minus n. Here you know that u of nt value is 1 from 0 to infinite, and minus infinity to minus 1 it is 0. So we can write this expression as k is equal to 1 to n ak sigma. I can write now it is from 0 to infinity e power pk nt. U of nt is 1 for this range, so remaining term is z power minus n. Once again, k is equal to 1 to n ak sigma n is equal to 0 to infinity. What you can write is pkt, I'll write it into whole power n, and z minus 1 whole power n. So this, if you simplify further, k is equal to 1 to n ak, n is 0 to infinity. What you can write here, this is e power pkt into z power minus 1 whole power n we can write. So you know the standard formula, if you have n is 0 to infinity and a power n, we can write it as 1 by 1 minus a. I'll use this formula to simplify this equation. So this is k is equal to 1 to n ak. So this is like a power n. So what we can write, this whole term I can write it as 1 by 1 minus e power pk t into z power minus 1. And we have started from this equation. Assume this is 1 and we got this h of z is, I'll write it here, h of z we obtained, this is sigma k is equal to 1 to n 1 by 1 minus, sorry, a into ak into 1 means this is ak by 1 minus e power pk into t z power minus 1. If you observe these two equations, for s is equal to pk, you can write this term z equal to e power st, right? So this is the relation between, or you can say the transformation from s to z. If you have a pole s, right, I can transform to z. So this will give the transformation from h of s to h of z. So what are the poles you have in s plane? I can map a particular pole into z.